Thanks, Melina. Yeah, so slight shift here in terms of theme. I'm going to be talking about direct imaging and astrometry, but it does fit in with this general theme of this session of ways that we can get around stellar activity here by using astrometry. So I'm really excited to share some results from a program I've led over my time as a grad student, where we're trying to efficiently image new exoplanets and measure their dynamical masses by leveraging astrometric information from Hipparcos and Gaia. So over the past couple of decades, an increasing sample of about a couple dozen wide-orbiting giant planets and about 100 or so brown dwarf companions have been discovered through direct imaging. And one of the main motivations driving these discoveries is determining how these objects form, right? How does nature produce a 10 Jupiter mass planet at a separation of 50 AU? Perhaps some of these planets are formed through kind of a bottom-up core or pebble accretion formation scenario. Maybe some of these planets are formed kind of through gravitational instabilities and massive protoplanetary disks. And maybe some of these planetary mass objects aren't forming like planets at all, but are instead the lowest mass products of the star formation process. And so kind of determining and kind of disentangling and determining sort of how these different potential formation channels collaborate to form the population of giant planets and brown dwarfs that we observe is one of the main overarching motivations behind exoplanet imaging. Now, in order to diagnose and test these different formation channels, we need to understand the kinds of planets that we're discovering. But one of the challenges is that for most imaged exoplanets, their masses are highly uncertain. This plot here shows the masses and orbital separations of the current sample of imaged brown dwarf companions in gray and imaged exoplanets in orange. Now, for most of these objects, their masses are kind of highly uncertain. We have to sort of infer them through evolutionary models, incorporating their luminosities and their ages. And so we may not be sure whether something is, for example, 5 Jupiter masses or 20 Jupiter masses, right? But as we march to sort of closer in orbital separations, the reflex motion that planets induce on their host stars gets larger. And so this has been used, especially in the last few years, to obtain a small sample of mostly brown dwarf companions, as well as a handful of imaged exoplanets with direct dynamical mass measurements. And these objects, these benchmark objects, really offer us some of the best constraints that we have on planet formation, as we can use these dynamical masses to test the evolutionary models that we have to use for everything else, but also their input assumptions about how planets form and evolve. But if we really want to use these dynamical masses to study planet formation, we just need a larger sample, right? We've just scratched the surface so far in the planetary regime. Now, one strategy to efficiently image new exoplanets is to leverage astrometry on their host stars from Hipparcos and Gaia. So the idea is that a wide-orbiting planet will induce a small proper motion change on their star over the 25 years between those two missions. And so one can use this to conduct an informed, targeted search for planets amenable to imaging by specifically focusing on stars that exhibit these small astrometric accelerations. And then an advantage of this approach is that those astrometric accelerations then enable the measurement of these rare and valuable dynamical masses. But how do we pick the best targets for an exoplanet imaging campaign? When given an astrometric acceleration, we can determine the companion masses that are consistent with causing it as a function of separation. If you plot this up in kind of mass separation space, you get this sort of characteristic curve where you have kind of a power law wide separations that kind of flattens out, and then you get these sorts of aliasing effects. Now this plot is actually for a star that hosts a benchmark brown dwarf companion. And so if I plot up the true dynamical mass of the companion and its separation, we see that it lines up quite well with this prediction. And so the point here is with these kind of predictions in hand, we can really effectively and quickly triage targets for an exoplanet imaging campaign. So for example, if we have an accelerating star whose prediction looks like this, we know that its acceleration could be produced by a brown dwarf within 500 milliarcseconds. If instead we see a prediction that looks like this, we know that we'd want to avoid this star for an exoplanet imaging campaign, as its acceleration can only be produced by a binary. But if we have an accelerating star whose prediction looks like this, we know that its acceleration could be produced by a planet within 400 milliarcseconds. And if the star is young, meaning favorable contrast ratios for imaging planets from the ground, this could be a promising target for an exoplanet imaging search. So over my time as a PhD student, I've been leading a high contrast imaging survey informed by these astrometric accelerations. This is a program that we launched back in 2019 at the start of my PhD with Gaia DR2. Since then, we've continually updated our target selection and our sample, all with the goal of maximizing the efficiency of imaging new planets amenable to these direct mass measurements. And so today I'm going to focus on the most exciting discovery from our survey, which is AFLAP-B. AFLAP-B is a imaged exoplanet that we discovered through our program that's the lowest mass imaged planet with a dynamical mass measurement. We first imaged this system in December of 2021 and then obtained follow-up imaging in February of 2023. We were able to confirm that the planet was co-moving with its host star. We also detected orbital motion that you can see on this GIF here. I've highlighted Jupiter's orbit here just to give a sense of the scales that we're probing with this planet. The separation between AFLAP-B and its host star is very similar to the separation between Saturn and our sun. Now, one of the most exciting elements of the discovery of this planet is that 3 teams leading similar kind of programs following up these accelerating stars all discovered the same planet at about the same time using kind of different instruments and kind of different data sets. Teams led by Rob DeRosa and Dino Mesa found this planet with sphere imaging taken in late 2022. And so this has meant that there's been an enormous amount of data on this planet kind of right from the outset. We imaged the planet with Keck, which gives us L-band photometry. We measured an L-band contrast of 10 magnitudes. The planet separation, when we observed it, was at 350 milliarcseconds. The planet's orbiting a sun-like host star in the Beta-Pic moving group, which gives us nice precise age constraint of 24 plus or minus 3 megayears. This is useful for testing evolutionary models with its dynamical mass. AFLAP-B follows in a tradition of planets being imaged around stars that host debris disks. So here the debris disk is kind of inferred from the SED of the host star, and so you kind of have to model it, but it has sort of a rough radius of 30 to 70 AU. Now the astrometric acceleration signal that led us and other teams to image the star and recover this planet is 2.5 meters per second per year. So this gives a sense of sort of the physical scale that's needed to access a planet like this. And then the big result, so updated orbit fits are showing a dynamical mass of 3.5 Jupiter masses, which places this planet as the lowest mass imaged exoplanet with a dynamical mass. Here's where AFLAP-B falls on the plot I showed earlier of the sort of sample of imaged planets, both with and brown dwarf companions, both with and without dynamical masses. And I think this plot really showcases how we as a community are marching closer and closer to imaging solar system-like planets on solar system-like scales. Follow-up science has already been happening with this planet since its discovery. In particular, I'll highlight this retrieval analysis that ZJ Zhang did only a few months after the planet's discovery, where he folded in all of the different data sets on the planet at the time, along with the planet's dynamical mass, and obtained this really intriguing result of a potential enhancement in the planet's atmospheric metallicity. And sort of subsequent analyses have kind of revised that down to sort of a more reasonable, kind of modest level, but still an enhanced level in the atmospheric metallicity. And so with all of this in mind, I got really interested in kind of mapping out the SED of this planet in this kind of 3 to 5 micron regime, with the goals of further characterizing the planet's atmosphere and testing this potential metallicity enhancement. And so these are wavelengths that we can get some of that, the wavelengths from the ground, but they're really wavelengths that are best observed from space, which means JWST. And so to this end, I co-led a Cycle 2 Director's Discretionary Time program with JWST to try to recover this planet with NIRCam at thermal wavelengths to test this potential metallicity enhancement and characterize the planet's atmosphere. AFLAP-B is at a really close separation to be imaged with JWST. JWST is extraordinarily sensitive, but it's a smaller kind of primary mirror, we're sort of longer wavelengths. And so that means that it's less than 2 resolution elements away from the host star at its current separation of 320 milliarcseconds. But there's another challenge that we have to contend with, which is that the coronagraph at the separation blocks out most of the light from the planet. This is imaging taken of the direct imaging early release science program target HIP 65426b. It's an imaged exoplanet that's at kind of a wider separation of 800 milliarcseconds. But even at that separation, the coronagraph blocks out about 10% of the light from the planet. But of course, we can work our way inwards from there. Here's a separation where 75% of the light is let through. Here's a separation where 50% of the light is let through. This is the nominal inner working angle of the coronagraph at 600 milliarcseconds. But we can go in further. Here's where 25% of the light is let through. And here's where 10% of the light is let through. And then here's where AFLAP-B falls. So in addition to trying to image this planet 2 lambda over d away from its host star, we're trying to do this in a regime where we're losing over 9 out of 10 photons to the coronagraph. And so needless to say, this is a really difficult detection to make with NIRCam. We're really pushing the instrumentation to its limits here at close separations. We, of course, convinced ourselves that we could do it. Here's a sort of what the prediction was that William, my co-PI, generated when we were submitting the proposal. But of course, you don't really know what your imaging is going to look like until you get on Sky, and we're in this like, sort of really challenging regime, right? Okay, so this is the prediction, and then this is what we observed. So we see AF-LEP-B right where we expect it to be at its current separation of 320 milliarcseconds at a high signal-to-noise, 4.4 micron contrast of 10 magnitudes. This is a really exciting kind of technical achievement for sort of space-based coronagraphy. The transmission that we're correcting for here is 7% at the planet separation, and this, of course, makes AF-LEP-B the closest separation planet imaged with JWST. And so, of course, we're extracting a ton of science from this data set. We can search for additional planets. We don't see any. But we can place upper limits down to sub-Saturn masses in the background limited regime. We, of course, compare our 4.4 micron photometry to other photometry that's been taken. It's relatively faint at these wavelengths, which points to deep absorption with carbon monoxide and carbon dioxide, which is, in general, kind of consistent with some combination of strong disequilibrium chemistry and elevated atmospheric metallicity. Okay, so I want to sort of turn at the end here to the orbit of the planet. We sort of course, carried out an orbit fit with the Discovery paper, but there's been some exciting updates since then, including this remarkable recovery of the planet in archival NACO data from 2011. And if you're wondering where the planet is, it's on the other side of the host star, because it was 10 years before the previous first data set. There's also been a gravity program that William Balmer led following up the planet. And so with all of this data together, we've kind of mapped out the orbit of the planet. We find that the planet's semi-major axis is 9 AU. The planet has a circular eccentricity and orbital inclination that closely matches the projected inclination of the host star, so some indications of potential spin-orbit alignment in the system. Dynamical mass of 3.5 Jupiter masses, which is consistent with hot start evolutionary model predictions, or warm start if the planet took some time to form. And in general, these sort of eccentricity and orbital inclination results are sort of reinforcing some of the emerging trends that we're seeing among the sample of imaged exoplanets. And so if we sort of sum these pieces of evidence together from the circular orbit, a orbital inclination consistent with spin-orbit alignment, a semi-major axis of 9 AU at the peak of gas giant production, an enhanced atmospheric metallicity, and all contextualized by this direct dynamical mass measurement of 3 to 4 Jupiter masses, these pieces of evidence as an ensemble are suggestive of the planet forming through core accretion. And so to go from the discovery of the planet to assembling such a well-mapped SED and orbit, and of course having this dynamical mass measurement, really speaks to the science that we can carry out with these surveys informed by this precision astrometry. And so with that, I'll splash up my summary points and take questions. Thank you.
Thank you, Kyle. Any questions from the audience? Start with Josh.
Hi, Josh Pepper from NASA headquarters. So you mentioned the spin orbital alignment. How do you know the angle of the inclination of the rotation axis of the star on the sky?
Yeah, that's a great question. So this is kind of the projected inclination of the host star, and so you can get that from if you combine an orbital period with a V sin I measurement. And so let's see, what's there back? Yeah, there's a back button. Okay, where is it? Okay, hold up. Right, okay, so the difference between those two values gives I gotta get the order right here. It gives a lower limit, upper limit? Okay, if the two values are very different, then that indicates that the orbit is misaligned. If they're similar, it's consistent with alignment, but it could also be misaligned.
Sorry, I just meant the 54 degrees. How do you know that precisely from V sin I? V sin I shouldn't be that precise. The 54 plus or minus 10 degrees.
Yeah, it's a high V sin I star. Yeah.
Okay.
Yeah, it has a V sin I of like 40 meters per second, something like that. Yeah.
Did you have a quick question?
Yeah, so.
Oh, microphone, here.
I should know better than that. So one of the cool parts is you have a mass completely independent of models. So have you been able to feed that back into the refinement of the models of these very young planets?
Yeah, that's a great question. I think that that's kind of a longer-term project here, right? And we've just scratched the surface so far, right? We have kind of a 3.5 Jupiter mass test point and a few more test points among the imaged exoplanets. I don't think it's kind of enough to sort of make ensemble arguments about kind of how effectively the models are kind of performing. Although that is something that perhaps could be done right now for the sample of brown dwarf companions with these dynamical masses. But yeah.
Thank you.
Great. Let's thank Kyle one last time. And if you want to pass it to Zoe.